Hi, I'm Mr. Franklin, and in this video, we're going to talk about inertia. There is another video where we talk more specifically about gravity and what it is and about weight, so you can check that out. But this one is specifically to kind of really lock in the idea of inertia for Newton's first law. So first, our first vocabulary word we need to look at is mass. Mass is a measurement of inertia in physics. That's how we look at it. Now, in more of a chemistry kind of standpoint, if you're in a chemistry science, you're going to probably think of it more like this, is it's the amount of stuff in an object. That's like the 5th grade definition of it. It's a pretty good one, actually, because stuff is made out of atoms. Okay, so the stuff that we're made out of is made out of atoms, and I can count the atoms and know the mass of an object with a high degree of certainty. Okay, so mass originally came from Newton, and it was a term to talk about how inertia works. But we have since figured out that atoms make up everything and we can count it. So it is a measurement of inertia based on counting the number of atoms. We also, in physics, we measure it in kilograms. Okay, so that's 1,000 grams. 1 liter of water is 1 kilogram. What's often confused with mass is this idea of weight. Weight is the force of gravity acting on the object caused by the mass of another object. So gravity is actually is a force caused by one mass existing next to another mass, and they actually pull on each other. Okay, that is weight. So the force of gravity is actually also known as weight, is equal to the mass times the acceleration due to gravity. So m times g, m times negative 9.8 on the Earth. Okay, so weight is connected to mass, but they're not the same thing. So we've got to be really careful when we're talking about inertia and things speeding up or slowing down and net force and all this, because weight is a force, but weight is not the object's inertia. There's a separation there. We got to keep them separate. So let's take a look at what I mean by this. So let's take a look at, let's use a bowling ball, for example, and our soccer ball that we've been using, okay? So to make it easy, to make the math easy, we're gonna pretend like we're gonna look at a microscope at the inside of the bowling ball. So bowling balls are heavy things, right? Okay, but let's say, for example, we count all the pieces and we count all the dots, and there are 20 dots inside this bowling ball. So I say its mass equals 20 dots. Okay, so the soccer ball filled with air, much lighter. You definitely would want to kick a bowling ball, right? So soccer ball has 4 dots for its mass. So that's how many pieces of it there are, if we were to count the atoms. Now I'm making a simplification because there's millions and millions and millions and millions of particles, okay? But we're keeping it simple. But let's pretend that's the mass of the object. So here I've got my bowling ball on the Earth, and so its mass, we said, is 20 dots. Well, the force of gravity is equal to mg, so if I took 20 dots times 9.8, I would get 196, and we will pretend that that's newtons. It's not really, because we're using dots instead of kilograms, but that's the weight of the bowling ball for this example. Well, let's take our soccer ball, put it on the Earth. It's got a mass of 4 dots, and 4 times negative 9.8 is, what is that, 39.2 newtons. So it has a weight of 39.2 newtons. Now look at this, almost 200 newtons versus 39, almost 40 newtons. A big difference, right? Okay, so this one's about 4 times heavier than this. So this is the weight of the object, and it kind of makes sense. Bowling ball, heavy, not so heavy. Now, if I go to the moon, I take my bowling ball, there's nothing to take apart or anything like that, so I don't change what the bowling ball is made out of, and I've got it here on the Earth, and then I go and I fly it on a spacecraft, and I land it on the moon. I haven't changed the bowling ball, so guess what its mass is? How many pieces of it are there? There's 20 pieces of it. There's 20 dots. So the mass is still 20 dots. It hasn't changed. The force of gravity on the moon is very different because the moon is much smaller than the Earth. And so we actually get a G for the moon of 1.66, 1.67, give or take. So my force of gravity on the moon is 20 times 1.67, which is, what is that? 33.4 newtons. That's the weight of the bowling ball on the moon. Oh my goodness, look at that. The weight is very different, but the mass is the same. Okay, so let's just check it with our soccer ball. So soccer ball, I take it up into space. We're going to pretend that we don't have any problems with inflating with the air and some of the things that could actually happen with that. But the pieces that make up the soccer ball is still 4 dots. So what's the weight on the moon? The weight is 4 times 1.67, which is, what is that? It's 66.8, or 6.68, sorry, 6.68 newtons. So it's way much lighter than the bowling ball, but it's also lighter than how much it weighs on the Earth, okay? And so weight is a very different thing, and it's a connection to gravity. It's a force caused by gravity. And so it's pulling it towards the center of the object it's sitting on, actually. But mass is just how many pieces there are. So let's think about it, though, real quickly in terms of inertia.